In general, probabilities are quite difficult to calculate. And so as a result, it can be quite helpful to summarize the different tools and techniques that we have for calculating probabilities as different rules. Now, one of the rules that gets passed around quite a lot is known as the addition rule for probability. And the addition rule for probability is really not so much a rule in and of itself. It's actually two different rules, two different principles that we can sort of blend together. And while it's helpful to keep in mind the addition rule, and while if you're studying probability, you'll likely come across the rule of addition, it's also useful to be very sure that when you are learning these mnemonic techniques, these memory aids to help you in your study of probability, that you're not just trying to do pattern matching, right? That you're really understanding where are these coming from, why do they work, what are the definitions underlying them. Because if you understand fundamentally what's going on under the surface, then you're going to have a lot better of a time remembering when do I need certain rules, when do rules apply, and similar concerns. So in particular, if we take the axiom of additivity and we take the arbitrary union property and we blend those together, then we'll often be able to call that the addition rule for probability. Now, it's useful, but it can also be the source of some confusion for students. So what is the addition rule for probability? Well, if we take two events, A and B, any two events that we like, then A union B has a probability given by the probability of A plus the probability of B minus the intersection, or the probability of the intersection. Now, if A and B are mutually exclusive, right, then as a reminder, that means that the intersection of A and B is the empty set, and the probability of the empty set is always 0. So if A and B are mutually exclusive, then we can cancel out this term, and we're just left with the probability of A union B is the probability of A plus the probability of B. In other words, the addition rule for probability tells us what's the probability that either A happens or that B happens, and we can get it in one of these two forms. Anytime that we're thinking of or-based probabilities, we should think to add. We're going to have to add up things. The probabilities are going to be growing. Now, under the surface, this is just the axiom of additivity, and the axiom of additivity tells us that if A and B are mutually exclusive, their probability is the sum of the two probabilities, and it's the rule for arbitrary unions. The probability of a union is the probability of A plus the probability of B minus the probability of the intersection. And so really, with the addition rule for probability, all we're thinking of is this is the probability of the union of two events, either mutually exclusive events or non-mutually exclusive events. Right? If we get ORs, the probabilities are getting larger. We're doing adding. So we can consider an example here of how this might apply. We're going to take a box. It's going to have 10 red cubes, 8 red spheres, 9 yellow cubes, and 6 yellow pyramids. One item is going to be drawn from the box at random. Each item is equally likely to be selected. And so we can first ask ourselves, well, what's the probability that the item that we draw is going to be a red cube? And so the way that we can solve this is by asking ourselves, well, how many red cubes are there and how many total items are there? And we know there are 10 red cubes, right? And then there's going to be 10 plus 8 plus 9 plus 6, right? So we have 18 plus 9 is 27 plus 6 is 33 total items, right? And so the ultimate probability that you draw a red cube is going to be 10 out of 33. And so to draw just a red cube is a fairly straightforward calculation. We look at the frequency of red cubes over the total frequency. Now, what's the probability that the item is red? And here, what we can think about is that this is actually a union, right? If we think about, well, to have red events, we want this to be the probability that we have red cubes, right? And so we can write that out as red cube, or that we have a red sphere. And so ORs are unions. We have a red sphere, okay? And so we want this event. So the probability red cube or red sphere, this is the same thing as just saying the probability that something is red. And notice red cubes and red spheres, well, they're disjoint, right? You can't be a red cube and a red sphere. And so we have that being the probability of red cube plus the probability of a red sphere. And we can work out both of those. We already found that the red cubes had a 10 out of 33. Red spheres are going to have an 8 out of 33. And so in total, that's going to give us 18 out of 33, right? So red cube or red sphere, we have red cube union red sphere, red cube plus red sphere in the probabilities. So that gives us 18 out of 33. Now, red squares, or red cubes and red spheres are mutually exclusive. If they could have something that was both a red cube and a red sphere, then we would have to be subtracting off. We'd have to use the arbitrary union rule. Okay, so we can continue. What's the probability that the item is a cube? Now here, right, we have red cubes, we also have yellow cubes. And so similarly, we want to know, well, what's the probability that it's a red cube or that it's a yellow cube? And we can add these up. Okay, so there's going to be, because they're mutually exclusive, 10 out of 33 are red cubes, 9 out of 33 are yellow cubes. So we have our 10 plus our 9 out of 33 gives us 19 out of 33. Now, what's the probability that the item is yellow or it's a cube? Okay, and so here we have 9 yellow cubes, right? We have 6 yellow pyramids, and we would have 10 red cubes and 9 yellow cubes. And so there's sort of two ways that we can do this, right? The first is just to say, well, if we want it to be yellow or a cube, that means we either want a red cube, we want a yellow cube, or we want a yellow pyramid, right? Those are the three possibilities. We'd go 10 plus 9 is 19, plus 6 is 25. That would give us our answer here. The other thing that we could do here, right, if we didn't want to reason through that whole process there, is we can say, well, this is going to be the probability that it's yellow, union, the probability that it's a cube, right? Because yellow or a cube is union, yellow union cube. So that's the probability that's yellow, plus the probability that it's a cube, minus the probability that it's a yellow cube, right? And so then here, what we're going to find is that the probability that it's yellow is going to be 9 plus 6 out of 33, right? These are always on 33. The probability that it's a cube is going to be 10 plus 9, right? Because there are 10 red cubes and 9 yellow cubes. So 10 plus 9 out of 33. And then the probability that it's a yellow cube, well, that's 9 out of 33. And if we work through all of this, we'll get the exact same answer. Okay, and so we can walk through those steps here. Yellow or cubed is yellow plus cube minus the intersection. 15 plus 19 minus 9, all out of 33, gives us our 25 out of 33. And so again, you could have worked this out directly or by using the rule for arbitrary unions. Now, what's my word of caution here? Students learning probability for the first time are often going to seek to apply the addition rule, or other rules for that matter, through pattern matching. Now, this might be effective in simple situations, but it's not going to necessarily scale well with more complex results. And so essentially, when you're solving a probability question, you're not just looking to decide, should I add here? Should I multiply here? What should I be doing? You should be trying to understand fundamentally what's going on, and then what are the fundamental tools that we need to solve this, right? That's going to lead to sort of much more rigorous answers and answers that are correct more frequently, right? I think that this is encouraged by referring to this as the addition rule, where often we're then thinking, okay, well, is this a case for the addition rule? Yes or no? If not, what's the other rule that we're using, right? Rather than thinking about the principles that are underlying this. And so my advice is actually to build familiarity with the set expressions, right? Understand how we can use set operations to represent our different events, and then understand how probabilities decompose over those set operations. And the axioms of probability, the secondary properties of probability apply to these set operators. So instead of just thinking the addition rule applies, we can think about writing down unions and then knowing if we have a union, what are the tools that we have for dealing with unions, right? It's going to scale up more nicely as the complexity grows. And so ultimately, we're not saying to do anything differently. We're going to add probabilities at the end of the day. But when you're thinking about this, it's useful for you to think about the addition rule is really just how do we deal with unions? And there are two ways that we can deal with unions, depending on whether they're mutually exclusive or not. Okay? So the addition rule for probability is going to provide a label for an important property of probability that would otherwise be captured through the axioms or the secondary properties. It associates itself with or statements. And so if you want the probability of A or B, we're thinking we're going to add up probabilities. But we really should take care to make sure that we're understanding the foundations of this rule, that we're not simply memorizing it and then trying to pull it out based on matching of patterns. We should really understand that the addition rule is actually the rules surrounding unions. And then we're just asking ourselves, well, when do we need to use unions? And if we understand when we have to use unions, then everything else falls into place from there.